It's part of a sort of program we've been carrying on for some time, and about entanglement and the fact that entropy manages to measure entanglement at least part of the time. So there's a little bit of a review in here, but also new stuff, mostly new stuff, about the fermionic states. And that's what I would like to talk about. Now let's see, how is this going? It's difficult. Oh, I can see it here. So this is a bit of an advertisement. Bosons are sometimes thought to be more complicated than fermions, especially with this group, because they can condense, and one of the problems is to find out whether bosons actually do condense, but that problem remains open. But condensed bosons that are in a product or coherent state, that's what condensed means. That means that the wave function is simply like this. Let's see, here it is, a simple product. Such a system, such a wave function is not entangled, or such a state is not entangled in any way by any definition of entanglement. So that is, from that point of view, not very interesting. Whereas fermions, on the other hand, are always entangled. And the reason they're entangled is the Pauli exclusion principle. That's something you just can't get away from. They always interact with each other. When I was a student, and I mentioned this to Piles at one time, Rudolf Piles, he said, well, a principle is not an interaction, but in fact it behaves very much like an interaction. And one of the problems we decided to address, and other people have also done so, is to try to quantify this. So our goal was to quantify the minimum possible entanglement, and as folklore might suggest, show that a pure Slater determinant, the state of a pure Slater determinant, in fact, gives the minimum entanglement by several definitions of entanglement. So if this is the case, then Slater determinants can be said to be the fermionic analog of boson condensation. Now, of course, physically they're very different, but they play the same role. And we sort of got into this working with Nicolas Rougerie, trying to understand what Di Finetti's principle would mean for fermions if it could be found, and we didn't find it, but we got onto this problem instead. Now, what we do is we study the bipartite density matrix of two fermions embedded in a sea of n fermions. So that's the usual situation. We're, of course, interested usually in the thermodynamic limit. Now, some of the results I want to talk about depend on n, the number of fermions, while others do not. A subtle but significant question, then, is what is n? Now, it is the number of particles, of course, usually taken to be the number of particles in a container. And the container is something we observe it sitting on the table, and it's a gas or liquid or whatever it is. But any electron in or out of the container is Pauli principle entangled with all the electrons in the universe. That's a fact. So is n equal infinity. This is not entirely trivial question. Let's see, how does this go? Yeah. The reason n is finite is that a physical state is really a state on a physically relevant algebra of observables, which in this case is the algebra of observables in the container. In statistical mechanics, one must always use the lowest possible dimensionality of a density matrix and not add superfluous degrees of freedom like color or flavor, which might exist but are not observable, to artificially increase entropy. This is something that used to bother me a long time ago, and then I put it away, and now it sort of bothers me again. Namely, if I take a gas and I want to compute its entropy, well, there are all kinds of degrees of freedom in there that I never observe, but which physicists tell us are there, like color, flavor, whatever, you name it. We don't count them when we compute entropy. So this is a little bit of a problem in statistical mechanics. Where do you stop counting, in a certain sense? But anyway, usually it doesn't bother us, but in principle it could. So now let me remind you, not everybody plays around with entanglement, so forgive me if I review a little bit what that is. So consider first a bipartite quantum system. So I'm just considering two particles now, or 2 degrees of freedom, or 2 whatever, doesn't matter. Anyway, there are 2 Hilbert spaces, and in our case they're the same. They're isomorphic, I mean. And there's a density matrix rho 1, 2 on this tensor product. And such a state, density matrix, is called separable if you can write it as a convex combination of tensor products. That is to say, you can always write any state in terms of its eigenvectors, but that's not very interesting here. The question is, can I decompose it enough to write it as a sum, which might be much bigger than the dimension of the space. If I can write it as a sum of pieces with positive coefficients, that's the important point, these lambdas are positive, so that each piece is just a simple tensor product. Now if I can do that, then I say the system is not entangled. But if I cannot do it, I say it is entangled. So that's the fundamental definition from the point of view of quantum statistical mechanics, or quantum information theory. Now the fundamental example of an entangled state is, of course, the E bit, the rho 1, 2 being a simple pure state. Let's see there. Yeah, a simple. It's funny. Yeah, there it is. A simple pure state. So rank 1. So this of course cannot be further decomposed. Anytime you have a pure state like this, it cannot be decomposed. It is what it is. And in this case, I take this vector to be the sum of 2 simple tensor products, 0, 0 and 1, 1, let's say if I'm in C2. So this thing cannot be written in the form of the first line with positive coefficients. And these are the kinds of states that one would like to have, because these are the ones that are entangled and cannot be disentangled. So that's the basic currency. Now if I start with a bipartite state, rho 1, 2, an arbitrary one, one can ask a couple of questions. And I've written a couple of questions here in the following way, but it requires a little bit of explanation. How many E bits does it take to construct rho 1, 2? Now what that means is the following, that you can take any state and apply a completely positive trace-preserving map to it. Those are the things you're allowed to do. You can apply such a map and get any other state you like. So going from one state to another is no great trick. But what is a trick is if you can do this with special kinds of maps, completely positive trace-preserving maps, which are called LOCC, that is to say, they operate on one factor at a time, or else they use what's called classical communication. I will not try to explain that, but the important point is there's a restricted class of operations you're allowed to do to a state, and in order to stay in the game. And the question is, can you construct the given state, how closely can you construct the given state using these allowed maps, starting with a tensor product of E bits. Now, by the way, when you do these maps, the dimension can change, so don't worry about that. And Conversely, you can ask, if I give you the state and I'm allowed to use one of these special kinds of maps, how many of these E-bits can I construct? So these are two measures which are of importance in trying to develop quantum communication or quantum computer or what have you. Now, it turns out that, there's a long song and dance that goes here, but it turns out that these questions can be quantified in terms of entropy. So I'm going to talk about entropy, but bear in mind that the entropy is, the interest of these entropies constructions really goes back to these questions. Okay, and these are called entanglement measures. So, next. Whoops. Oh, sorry, wrong button. Okay. So, now, we all know about, so these are a bunch of theorems about entropy of states for fermions. So I remind you that we're talking about fermions now. So we all know subadditivity of entropy. So I look at this two-particle state, and by taking partial traces, I get, of course, the one-particle states from them. And the subadditivity of entropy, which is one of the basic facts of the world, says that the sum of the entropies of the one-body states derived from the two-body state is always bigger than the entropy of the two-body state. So in other words, interaction always lowers entropy. And the only way you can get equality in this is if the two-body density matrix is a simple tensor product. Now, I want to repeat, I'm not talking about pure states now in general. I'm talking about a general state. The pure states are not very interesting from our point of view. Well, this kind of equality cannot happen for fermions. Why? Because the states have to be, the rho 1, 2 has to be antisymmetric, so it can never be decomposed in such a simple way, because any decomposition of this kind, rho 1 tensor rho 2, is not going to be antisymmetric. It might be symmetric, but it will never be antisymmetric. So the question is, what's the minimum amount by which you get inequality in this subadditivity? By the way, it has a name. It's called mutual information. All right, so it turns out, here's the theorem, that this mutual information is bounded from below by this logarithm of 2 divided by 1 minus the trace of rho 1 squared. And rho 1, of course, has trace 1. Rho 1 squared will, of course, have trace less than 1. So that everything is positive. It makes sense. This is a sensible expression. And here's the second part of the theorem. There's equality in this inequality if and only if the n-particle fermionic state is a pure state Slater determinant. Now, I didn't mention the n-particle state, but what I'm thinking of now is that I have an n-particle fermion state. My n could be 2. It's certainly bigger than 1. And I look at the two-particle reduced density matrix, that is, I look at two fermions in this box, and I ask, I have first an inequality that says something about the mutual information of the two, but when can that be achieved? That can be achieved if and only if the n-body state from which I derive these two is itself a Slater determinant, whatever n might be. So that's the theorem. And not a convex combination of Slaters. That won't do it. So that's the theorem. Now, there's something to be said about the significance of this. Recall that for n fermions, of course, by symmetry, rho 1 equals rho 2, or antisymmetry, and that's bounded by 1 over n times the identity. Now, there's a question here of convention. Let me point it out that in many body physics, you usually don't divide by n. That is, the trace of rho 1 is n usually, but now I always want to talk about density matrices whose trace is 1, so I have to divide by n. That's why you get 1 over n times the identity. And so all the eigenvalues of rho 1 are less than this number. And this number, this becomes an equality if and only if the big n particle state from which this thing came was in fact a Slater determinant. And in that case, S1 equals S2 equals log n, and S12 is log of n choose 2. That's what happens for a Slater. Okay, so here's the proof. So this is now a new general non-fermionic theorem about a bound on subadditivity. I don't know if this has appeared before. It's not all that hard to derive, but here it is. So this theorem that I'm talking about now works for everything, not just for fermions. It says that the mutual information is always bigger than or equal to, let me go to the right-hand side. It's bounded by the trace of the following. You take the square root of rho 1, 2, which is given. Rho 1 and rho 2 are given. And you take the square root of the tensor product, and then you square the whole mess. It's very hard for me to see this light. That is a lower bound for the mutual information. Now, we will apply this later to the fermionic case. So this is a general theorem, and here's the proof. It's very simple. You start with the Piles-Bogoliubov inequality that says the trace of e to the minus h plus a, assuming that the trace of e to the minus h is 1, usual thing in statistical mechanics. The perturbation shifts the partition function at most by e to the trace of the e to the expectation value of a with respect to h. That's a well-known and ancient fact. Now, let's do this with h equals minus log of rho 1, 2. And a is this combination of logarithms over there. And when you work it out, this difference with a half. Now notice I'm putting a half here. It's very important. With this difference, what is it? I've lost something. Is bounded by. Sorry, I'm going to look. This is a non sequitur. Sorry about that. So I'm going to look at this quantity and take e to this delta and use the Piles-Bogoliubov inequality and the Golden-Thompson inequality, which says that the trace of e to the a plus b is less than the trace of e to the a times e to the b. And here it is, worked out in detail. The trace of rho 1, 2 times these logarithms, which is the difference of the entropies. That's the mutual information there, except for the half. And that's less than using Piles-Bogoliubov and then using Golden-Thompson. I end up with this. Golden-Thompson is the last line. And this thing, this combination of operators is just this, the trace of it is just the same as the trace of that. That's just an identity, and this proves the theorem just by taking logarithms. Now, for fermions, this quantity can be bounded in the following way. This quantity over here. Use the Schwarz inequality on the left side. Here it is over here. And this would be the trace of that times the trace of that. But now, here's where the fermionics comes in. Up to now, everything's completely general. The fermionics comes in the following way. Rho 1, 2 is a fermionic state by definition, and so by definition, it's antisymmetric. The second factor is not antisymmetric, it's symmetric. So that is to say, it's not symmetric, but it's I have to apply this tensor product to an antisymmetric state. So I'm allowed, if I wish, to put in a projector here and here, which is the projector onto two-particle antisymmetric states for free. So when I do that and use the Schwarz inequality, I get that this object is less than the trace of that is 1, and the trace of this thing with the antisymmetric things is something that you can work out. And you get, when you do this, you have to fiddle around, but basically it's a bunch of identities. You eventually get theorem 1, which I'll remind you says that the, yes, it's up there. Sorry, go back one more. Here it is. It says that this mutual information is bounded from below by this quantity, and that's not 0. So that's the first example of a theorem, a little theorem. It's not a big deal, but it's a little theorem that says that fermions have to have a certain amount of inequality in the subadditivity inequality. So that's our first result. Second result is, let's look at the entanglement of formation. Now, this is this is supposed to be a quantitative measure of the entanglement of the two particles. So up to now we said about entanglement that a state is entangled if and only if you cannot write it as a sum of simple tensor products. And now we want to quantify that. And the quantification EF, which I will describe in just a second, is supposed to be the number of E-bits you have to use to create the state. Remember I said there were two quantities. One is the number of E-bits you have to use to create a state, and the other is the number of E-bits you can get out of a given state. So this guy is supposed to represent, and there's a long story that goes with this, which I will not give you, that says that this number, which I'm about to compute, measures the amount of E-bits I need to form the state. And it's defined in the following way. You split up the given state, rho 1, 2, into a convex combination of states that you like. They don't have to be simple rank 1, that is, they don't have to be pure states, but they will be by concavity, so think of them as pure states. So you split up rho 1, 2 as best you can, and then compute the trace of these are now in the tensor product, and now you compute the partial trace over one of the particles. That gives you a density, single particle density of one of those states, and then you add up all the entropies with the convex combinations that you invented, and you take the infimum of that over all possible ways of splitting up the state. That's called the entanglement of formation. And the theorem is going to be that this quantity, which could be 0 in general, is bigger than log 2. And for fermions, and there's equality if and only if rho 1, 2 is a convex combination of pure state Slater determinants. That is to say, the state is fermionic separable. And fermionic separable, remember, separable meant that you could take a state and write it as a convex combination of simple tensor products with positive coefficients. So you cannot do that for fermions. But what can you do? Well, what this theorem is telling you, that the best you can do is write it as a convex combination of Slater determinants for two particles, and then compute the entropies of that. So again, Slater determinants win, so to speak. And that means after you subtract the log 2, what you're left with, if you take this quantity, which could never be smaller than log 2, if you subtract log 2, you get a quantity which I would call the entanglement of formation of two fermions. And this difference is 0 if and only if the state you're looking at is a Slater determinant or a convex combination of Slater determinants. And therefore, this theorem tells you that this quantity, this entanglement minus log 2, is a faithful measure of fermionic entanglement. The only way it's going to be 0 is if the state you've got is a convex combination of Slater determinants. So it's a bit like saying for bosons, the minimal entropy state or entanglement state is a simple product. Here it's, or a sum of such. Here it's a sum of convex combination of Slater determinants. So in this sense, Slater determinants are the basic coin for fermions, and this is a faithful measure of entanglement. Now, let's see how. So recall that the entanglement of formation is this infimum, which is over here, and to prove that it's bigger than log 2, it suffices to prove that if rho 1, 2 is any fermionic density matrix on the antisymmetric tensor product, remember fermions, antisymmetric tensor product, and if rho 1 is the trace over 2 of rho 1, 2, that is, it's the one-body density matrix, then the entropy of rho 1 is bigger than or equal to log 2. That's enough to do that. So any pure Slater has, in fact, that S of rho 1 is bigger than or equal to log 2, and so does a convex combination of pure Slaters. So Slaters would minimize if we can prove that, too, that the entropy of rho 1 is bigger than log 2. Now, by theorem number 1, the subadditivity theorem, and since the entropy of rho 1, 2 is, of course, never negative, and since S of rho 1 equals S of rho 2, we have that. I'm just rewriting what the subadditivity theorem said in this particular case. It says that twice the entropy of rho 1, I'm just adding rho 1, S of rho 1 to both sides for reasons of best known to myself. So it says that 2S of rho 1 is bigger than S of rho 1 plus this stuff that I had from theorem 1. It looks familiar. And now by Jensen's inequality, e to the minus s of rho 1 is bigger than or equal to the trace of rho 1 squared. That's just Jensen. And if I call x, call it trace of rho 1 squared, let's just give it a name, then from 3 we have that 2s of rho 1 is bigger than the inf of all, bigger than whatever this could be, which is this quantity over here. And a simple calculation shows that the minimum is achieved at x equal 1/2, which yields the required statement. So that proves theorem number 2. Now, theorem number 3. Are there any questions so far? I'd be happy to. You're not the only one, I'm sure. Yeah. Yes. Yes. So. I'm not following you. So can we do this later, huh? Yes. Right. Didn't I say that? Sorry. Oh, here. Let me think about that. You could be right. Yeah, well, that's what I said. We want, it suffices to prove this, but it's a fact. Any pure Slater has this property, and so does a convex combination of Slaters. In fact, anything does. Oh. Huh? Okay. I think it's clearly, I don't think, well, okay. So maybe I proved something twice. All right, go ahead. Yeah. Yes. Yes. No. I mean, the definition simply of an entanglement of formation is you just break it up. That's just the definition. I mean, I didn't invent the definition. That is the definition, that you break it up that way. What? Yes, it does. You want to put on an extra condition. Yes, but I'm just, sure. Yeah, I mean, if you want to do it, you're free to do it. But the definition, as stated in the books, is that you just take decomposition of row 1, 2. You could also look at row 1, 2, 3, and so on, continue in this way. But the definition is the definition, and that. What can I do? All right. So let me go on. So where are we? So theorem number 3. So consider the entropy of a two-particle density matrix of an n-particle fermion state. So row 1, 2 has n choose 2 eigenvalues for Slater, and the eigenvalues are 1 divided by n choose 2, and therefore the entropy is 2 log n minus log 2 for Slater. Now, we can ask, how can we minimize S12, given that this row 1, 2 comes, it's in the line of what you were asking, it comes from an n-particle Slater, from an n-particle state. We do not know which which n-particle state actually minimizes S12. That's an open question. We could not prove it. What we can prove, and I don't think anybody else has either, it seems sort of obvious, but we don't know how to do it. And you'll see why there's a difficulty in just a minute. We believe that, we can prove the following, that the two-particle reduced density matrix of any n-particle fermionic state will satisfy the following, that S of row 1, 2 is bigger than 2 log n plus something of order 1. We can prove that. The conjecture is that for any n-particle state, for the Slater it's 2 log n minus log 2, but if I take any other state, the entropy is bigger than this quantity. And therefore the Slater is at least asymptotically close to the minimum, but we don't know how to prove that the Slater is the minimum, and you'll see in just a second why this is problematic. Okay, so to summarize at this point, the entropy of a single fermion satisfies that S1 is log n, bigger than log n. This is the statement that Robert alluded to, because the eigenvalues, the biggest entropy, the lowest entropy would be when you have a Slater. And we know that. And we know that the entropy of row 1, 2 is bigger than or equal to 2 log n plus order 1, which is satisfied by any Slater. And this is not a proof now, this is a commentary. The n dependence in the factor of 2 is very interesting for the following reason. There's a 2 in front of the log n. Recall that while the eigenvalues of a fermionic one-body density matrix are characterized by the eigenvalues are less than 1 over n, there is no simple characterization of the eigenvalues of a fermionic row 1, 2. This is one of the great mysteries. It would nicely solve the many-body problem if we could figure out what the bounds on the eigenvalues of a two-body density matrix are. We just don't know what they are. We have some bounds, of course, but we don't know a complete characterization. For the one-body density matrix, the complete characterization is that the eigenvalues are bounded by 1 over n. We know that. But for 2, we don't know what the characterization is. Now, a long time ago, C.N. Yang showed that the upper bound is not what you might think, 1 divided by n choose 2. That is not the upper bound. So you would think that if the eigenvalues of the two-body density matrix might be should be reflect what you know about the one-body density matrix, namely they're bounded by 1 over n. So this would be a natural guess, but this is completely wrong. In fact, the largest eigenvalue can be as much as 2 divided by n minus 1. So the first guess, n choose 2 inverse, is 1 over n squared, essentially. But what Yang showed by example is that it's less than or equal. It can be as big as 2 over n. It's a big difference, n and n squared. So suppose, and this is of course what makes BCS theory work, that you have these huge eigenvalues of the two-body density matrix. Now, this was a very interesting and famous paper in Reviews of Modern Physics, and but somehow it seems to have gotten lost. But it should be. It's a beautiful paper, and he works this out for the first time, and he actually constructs this eigenvector of the two-body density matrix with this eigenvalue. So now, let us suppose that you could have lots of eigenvalues of this size, 2 over n, in your two-body density matrix. He gets 1, but suppose you had a lot of them. And suppose you exhausted the entire spectrum with eigenvalues that are that big. Then the two-body density matrix would have a low entropy. If you had just a few large eigenvalues, that such a thing has a low entropy. But this doesn't happen, because the theorem up there says S12 is bigger than 2 log n, says that the 2 is the crucial number. If you just had Yang states, you would just get a log n. Remember, the 2 is the power. So to say that it's at least 2 log n means that if you could have several of these Yang states, but not too many, and you have to have lots of small eigenvalues to give you the extra 2, go from 1 to 2. And as far as I know, that's not been noted before. And where this comes from, or rather, why this a few small eigenvalues can change things, is, remember, we're looking at the function x log x. That's the entropy, x log x, trace of rho log rho. Now, x log x is something that starts off with an infinite slope. Right? You go, minus x log x goes this way. It's concave. Anyway, it starts with an infinite slope. So small eigenvalues really dominate, or can really dominate, the entropy. Tiny, tiny eigenvalues, lots of them. They give you a huge boost. And that's what this theorem is saying. Okay. So let me go on. That's the commentary. Now, this is one more topic. I'm not going to go back to the previous one and prove it. So now there's another kind of measure of entanglement, which is called the squashed entanglement. It's defined completely differently from the entanglement of formation. This is supposed to be, according to the inventors, I think this is Christandl and Winter, and I'm not sure who else. Oh, Tucci. Tucci, yeah. In fact, when we wrote this paper, or a paper involving squashed entanglement, we got a heated email from Mr. Tucci, who said that he invented this first, and he put it on Wikipedia, and he was right. He did invent it first. So the way this one goes, and this is supposed to be reflect how many E bits you can get out of a density matrix. Remember, the entanglement of formation says how many E bits you need to make a state, and this is supposed to have something to do with how many E bits you can get out of a state by a completely positive trace-preserving map with LOCC map. And it goes as follows. You invent a third Hilbert space, any one you like, And you take on this Hilbert space, you take a row 1, 2, 3. Sorry, I did it wrong. Where are here? You take a row 1, 2, 3, whose partial trace over 3 is the given row 1, 2. You do this any way you like. And then you subtract from, you compute the entropy of that. And you also compute S3 in an obvious way. And you take the difference between those sum of those two things and S13 and S23. So I guess the meaning is clear, what all these things mean. This quantity is positive, no matter what you do. And the reason it's positive, that's the strong subadditivity of entropy. And so it's positive. And now you try to take the infimum of that, of this positive quantity, over all possible ways of sticking on this third space. Okay. Now, it turns out, and this was a theorem actually of, I think, Christandl and Winter, who actually proved this. I don't think Tucci did, but they did, is the following, that this squashed entanglement is strictly positive unless row 1, 2 is separable. Now, remember what separable means. Separable means that there's no entanglement. It means that you can write the state as a convex combination of simple tensor products. So, so this quantity, this whatever this infimum is a faithful measure of entanglement. And it's also a theorem that this squashed entanglement is less than the entanglement of formation, which I defined before. Okay, so it's a quantity that's a faithful measure, and so is the EF, but it's below EF. Now, this is a big surprise. What comes next? We conjecture that the minimum squashed entanglement for a fermionic density matrix rho 1, 2. Remember, rho 1, 2 is arbitrary but fermionic. And we're trying to compute its squashed entanglement. We conjecture that this minimum occurs for Slater determinants. We don't know how to do that. And we also don't know how to compute the squashed entanglement for Slater even. Here we really don't know how to do anything. You might think that for a Slater determinant you can compute anything, but no, you cannot compute the squashed entanglement. At least we don't know how to do it. However, our conjecture is that you take a Slater and then you can compute for a Slater what the squashed entanglement would be, and you come up with this peculiar thing. Now look at this. It says the squashed entanglement is very small. Log n over n is essentially log of 1. So in other words, it's of the order of 1 over n. Very small. It's slightly different if n is odd. This is a conjecture, and we were not the first. It took us a long while to see that this was what would happen, and we also noticed that it was also done. I didn't write it here, but yes, I did write it. In fact, it's also done in this by Christandl, Schuch, and Winter. Now, so at first we thought that the minimum was the same as for the entanglement of formation, remember, which was bigger, it's of order log 2. And this is not true, it's this quantity. It's at least this big. And I mean, yeah. Now the way this was done, the way it is done, is the following, and it's very weird. You want to, given rho 1, 2, you want to invent a state of n particles with a very low value of the squashed entanglement. Or put it another way, you really want to invent a Hilbert space H3 to make this squashed entanglement as small as possible. And it turns out that this is a little bit obscure, but let me explain it. It says what you do is contrary to your intuition. What you do is you take the Slater determinant of n particles, where n is a really big number, and then you look at the state of n over 2 particles, the n over 2 particle density matrix of an n particle Slater. So that's now sort of a complicated thing. It's, even though you started with a Slater, it's the n over 2 particle density matrix is sort of a big, huge mess. You look at that, and that's going to be your H3, or your H123. And if you take that, it's very non-intuitive. It's almost counterintuitive. But if you do it, you end up with the quantities that I wrote on this line. So, and that's the thing that gives you this very small squashed entanglement. And no. I mean, yes, if I do this thing, yes, n over 2 is the optimal, but I don't know if the whole scheme is optimal. So now, one other thing. So I just wanted to mention an inequality that is not exactly about entanglement, but it's about entropy. And well, let me just mention it. So, so I'm going to use the Piles-Bogle-Lyubov inequality the way I did it before, and the Golden-Thompson inequality, but that doesn't work because I want to talk about 3 density matrices. And what do I want to talk about? I want to talk about the monotonicity of relative entropy. Relative entropy, of course, just to remind you, is the following. I take a density matrix rho, any one you like, another one sigma, any one you like, and take the trace of rho log rho, which is minus the entropy of rho, and add to that, so to speak, rho log sigma, sort of a funny entropy and of sigma with respect to rho. So this is the relative entropy definition. And this definition, of course, was very much used in classical probability theory. In quantum mechanics, it was invented by Umegaki. All right, so we want to look at that. And now the big theorem in this subject is that this relative entropy increases if you add on another state. Oh, sorry, I've got it the other way around. If you contract, that is, if you take a trace, take a partial trace, the relative entropy goes up. That is, if you smear things out, entropy goes up. So the theorem is, so d of rho 1 sigma 1 is, of course, bigger than d of rho 1 2 sigma 1 2. These are the rho 1 and sigma 1 are the partial traces, and the lower bound is given by this formula that you see in blue. And now, so the question is, an old question was, that was worked out by Ruskay, is when do you get equality? When does the relative entropy not increase? It could be that they're equal, even though rho 1 2 is not the same as rho 1 and so on. It's not a simple tensor product. And the answer that Ruskay came up with is what you saw here, that this very strange formula. It says rho 1 2 minus the log of sigma 1 2 is equal to the log of rho 1 minus log of sigma 1. Sorry, there should be a logarithm here. Excuse me, that's missing. Is equal to the log of rho 1 minus the log of sigma 1. This required identity is not so easy to achieve, but that's the condition, necessary and sufficient condition. And in order to prove that, one needs to use this triple matrix inequality. It's the analog of the Golden-Thompson inequality for 2 matrices. Here it is 3, the trace of e to the a plus b minus c instead of e to the a plus b. Remember, Golden-Thompson just says that you can separate things and the traces go up. There's no such analog for 3 in such a simple form, but there is in this form. And I wanted to advertise that triple matrix inequality because it does identify this problem, and that's a necessary and sufficient condition. Okay, and well, I guess I've run out of time, so I will not do this. And but thanks for listening.
So thank you very much, Elliott. If there are questions, then we are supposed to record them. So bring the microphone.
You get some exercise.
I have a question about the squashed entropy. The requirement for the space H3 that is tensored to the other one. I mean, this is all part of a big fermion system, right? So
no,
it's
H3,
also,
no.
H3 can be
anything.
So it can be, it's not the anti-symmetrized tensor product
right.
multiplied to
That's
H1
right.
times H2.
That's right.
Okay, so that was the question.
Again, that's the definition. Now, you might want to say I should put a restriction on it, but now you're shaking your head no. Yes, or... Huh? Yes, okay.
I mean,
true.
if it was an anti-symmetric tensor product, then I would think the only row 1, 2, 3 that yield a pure Slater determinant state would be Slater determinant, pure Slater determinant states itself on a bigger space.
I'm not sure.
Yeah,
I'd have to think about that. I something tells me that's not right, but I don't know. I don't know.
I mean, these are very rigid states, the pure Slater determinants. So.
Okay. So further questions? Well, we already had some, of course, during the lecture. Well, does not seem to be the case. Well, of course, Elliott is available for private discussions, I suppose. So, thank you very much again.